So we're starting with the idea of charge, and you've worked with charge a lot in chemistry. So what is it? Without looking at the notes. Okay, positive or negative, that's a good start. What else do you know about charge? Opposites attract. What else do you know? Oh, you're reading the notes now. Okay, so charge is when something has a different number of electrons and protons. Because, of course, electrons and protons carry electrical charge. As long as an object has equal numbers, those balance and it's neutral. It's electrically neutral. If we have an object that has more electrons than protons or more protons than electrons, suddenly the object itself is charged. So you have known since, I don't know, the 6th grade, the last time you were using word banks, that electrons have a negative charge, protons have a positive charge. If we wanted to positively charge an object, what would we have to do? Oh, never mind, it's in the notes, you can read it. We have to strip electrons away from it, yes. And there are a lot of materials that will give up their electrons happily.
It's funny when I have a balloon and I do that and it just sticks to the side of my face.
Okay, so we know all these things about charge, and we know that it's conserved, as somebody mentioned, and we know that means that we can transfer what? We can transfer charge. Electrons. Are we ever transferring protons? No. We're only
nuclear explosion.
Well, yeah, and then we get into nuclear explosions, and it all just gets ugly and goes downhill from there. We transfer electrons. We never transfer protons. That's really important to understand, and I think you guys all have a grip on that from chemistry. If you don't, we need to go back to chemistry. So, and you know that opposite charges attract, and like charges repel. What was happening over there? That's so weird.
Opposite charges were attracting.
So weird. Okay, so we can transfer charge from one object to another, and we do this all the time. And we actually just did it over there. So there are some materials that are really good at allowing charge to flow, which means that electrons flow freely onto or off of the material. Those are conductors. Name me a conductor. Okay, copper. Metals in general. And if you think back to chemistry, why do metals permit free flow of electrons? Why? Good question. Because their whats are also close? No, the atoms in salt are very close too, and sodium chloride.
No, but they are.
Hey, Dylan, aren't you in chemistry? So we've got the materials that permit flow, conductors. We've got materials that stop flow, insulators. So we said conductors will conduct because, for whatever reason in their chemical structure, the electrons are not in fixed positions. They're wherever they go is fine. Yeah, sure, be home by dark. What about conductors? So what kinds of materials are good conductors? Things that are covalently bound are doing what with their electrons? They're sharing them. If you and I are sharing a plate of cookies, what are the odds that we're going to let somebody else, some other stranger, walk off with the cookies? Pretty low. You know, if you and I are sharing the cookies, we're going to keep that plate of cookies right between us. It's not going anyplace. Hands off my cookies. Materials that are held together by covalent bonds tend to be lousy conductors. They tend to be good insulators. They're sharing those electrons. Those electrons are localized. They are located in a specific place between the nuclei of the atoms.
Is there any element that does not have take a charge at all?
So we can take a conductor or an insulator and we can charge it by contact. So we can take one charged object, touch it to another charged object, and dump electrons onto something, or in some cases pull them off. More commonly, we can pull them off, and the image there is, you know, an example of charging by contact, both positively and negatively. Now, can you remember all the way back to physical science, which I think you took as freshmen for the most part? Through ways of transferring heat. Remember those? 4 ways of transferring heat. Okay, I heard convection. I heard what else? Conduction, radiation. That's it. That covers it. Okay, so we're going to talk about contact charging. If you think about heat conduction, a snake laying on a rock in the sun is warming itself by conduction. The surfaces have to be in contact. So thermal energy is flowing from one surface to the other via contact between the atoms and molecules of those objects. In conduction charging, it's the same principle. We have to touch the thing that we're charging. So when I took the rabbit fur and rubbed it up and down on the acrylic rod, and obviously the rod ended up charged, that was, well, that was actually triboelectric charging, so strike that. Sorry. But we had a charge on that rod. I could discharge the charge on that rod to a third object. Okay? If I touch that rod to something else, the charge in the rod goes away. Because I have just either pulled electrons off or dumped electrons on to that third object. That's conduction charging. Now, when we charge things by conduction, so if this object has an excess of electrons, I've added electrons to this object somehow, and I touch this object, and now they're both charged. Do they have the same charge? Yeah. Because some of the excess electrons flowed onto here until this one was lower charge. And you can think about the sort of relationship of potential energy. Things want to be at a lower energy because it's more stable. So this one will lose some charge until it's more stable, and this one will gain some charge. You can think about your battery discharging. If you've ever had a battery that, even sometimes dirt on the surface of a vehicle battery will provide a pathway for the battery to discharge. So that's all conduction charging. Time is it?
As long as missing.
All right, so the other way that we can charge something is by induction. So when we induce a charge, we don't have the two objects in contact. Have you heard the term ground?
Yes.
Okay. In schematics, and we're going to do schematics later, ground is symbolized by that symbol.
Doesn't look like ground.
Well, what that is a pathway.
That's a ground, you're a bad drawer.
Okay, that is a pathway to ground, and that's the symbol that we use to represent a ground in an electronic circuit. We call it a ground because it's most literally the earth itself. Okay? When we want to charge something by induction, we have two objects, and we somehow add electrons or remove electrons from this one. This one has to be connected to some reservoir. We get back to this idea of reservoir. Some reservoir for electrons. What is the ultimate infinite source and reservoir for electrons? You're standing on it. The Earth. So, the Earth is made up of all these billions of atoms, googleplexes of atoms, with all of their electrons. And many of the materials in the Earth will allow electron movement. So if we have this object that's charged and this object that's neutral, but is connected to the ground somehow, if we bring this one close to this second object, not touching, but close, then so if this has got excess electrons, this one we will essentially push the electrons off of. Okay? Because like charges do what? Repel. So we'll push the electrons off of this and down into the ground, whatever we're using for ground. And if you've ever, who's jumped a car? Who's jump-started a vehicle? Okay, you should all do that. You should all know how to do that. You always ground, and you are creating a reservoir for electrons to be drawn from or provided to. Okay, so we've got a house here, and the green thing sticking up on top is a lightning rod. I drew it in green because lightning rods are typically made of what material?
Copper.
Copper. Usually it's a copper rod on the top of the building. That copper rod is connected to a cable, and that cable runs to a big spike driven into the ground because that is the ground. So the lightning rod attracts lightning and sends it into the earth where it can't burn your house down. Okay? Ground is very attractive. It's an infinite reservoir.
Ben Franklin.
When you charge by induction, would the charges be identical?
Yes.
Maybe.
This is awesome. You guys don't know.
We have no idea.
Okay, so let's think this through again. So when you charge by induction, you induce an opposite charge on object 2. Induction always involves 3 objects. Object 1, your charged object. Object 2, the thing you're going to induce a charge on. Object 3 is what? Ground.
So,
Some reservoir. Now, on cars, there's a ground strap on the battery. Where does the ground strap go? Frame. Has to go to a steel frame. A large hunk of steel is a pretty good reservoir for electrons. Okay? So that's that idea of anything that's grounded literally goes to a reservoir of electrons. It doesn't literally have to be the ground, but it's got to be something that's substantial enough, that's got enough atoms that it can serve as a, we call it an infinite reservoir of electrons. Obviously, the frame of a car is not an infinite reservoir, but in the scope of the number of electrons that are moving, it's pretty big. Okay, the last kind of charging that we're going to talk about, this isn't really true charging. This is just polarization. So think back to chemistry. What's a polar molecule? Some of you don't have to think very hard or far back. Polar molecule is what? A polar molecule has got areas of surface charge. It's a partial charge. So if we think back to water and we think back to Mickey Mouse, Mickey's got positive little ears and a negative little chin, which is a stupid way to remember it, but you'll never forget it, I hope. So that's a polar molecule. When we polarize something, we create partial charge. So this is not a true charge. We're not removing any electrons from something. We're not adding any electrons to something. This is typically observed in insulators. Why? Why would this be something we would see in insulators and not in conductors? So we're not actually having any electrons leave or jump onto the object. And remember, that's what conductors prevent. Conductors do not allow electrons to flow on or off the object. Insulators do not allow electrons, thank you, to flow on or off the object. But they'll allow them to rearrange themselves. Okay? So we take a surface that's an insulator, and it's got areas of positive and negative charge potentially. We've got protons and electrons. If we bring something that is charged near the surface, what happens? These can't leap off and they can't leap onto the other object, but they can line themselves up. So suddenly, if these are all electrons, it can arrange itself so that all the protons are here and all the electrons are here. And it's considered a surface charge because you do actually have a charge on the surface, but it's not a real charge, it's not a full charge, and the minute you take this away, this is liable to break right back down. So it'll hold for a while, and it depends on the material, but it will hold for a little while.
When you put like
math problems we'll do today. So we're going to talk about electrical force. We've talked a lot about forces. You guys know all kinds of things about force. And you know, if you have ever had the experience of opening a plastic bag or dry cleaner plastic, it's a thin plastic film. It sticks to you. It's, you can get like all wrapped up in it.
It doesn't let you go.
Well, obviously there's some sort of force attracting it to you. There is an actual force, just like the force of gravity, just like normal force, just like any other force we've talked about, there is a force that is adhering that thin plastic film to your hands, to your, to your hair, to whatever else. So electric force is actually the force of, well, it's the force between two charged things, between two charges. And what's different about electrical force than any other force you've studied? So, gravitational force. Even though when we talk about acceleration due to gravity, it's negative because we use down towards the Earth as negative. Gravitational, is there anything that's repulsed by the gravity of something else? No. Gravity is always attractive. Always, always, always attractive. So, you are attracted to the Earth is attracted to you. This magnet is attracted to the Earth is attracted to the magnet. All of the things that are affected by gravitational force are attracted to other things based on gravity. Electrical force is a little bit different because it goes two directions. It can be attractive or repulsive. So when you get an answer for something that is force electric, you can have negative electrical force, which is repulsive, or you can have positive electrical force, which is attractive. And you got to pay attention to your signs. So with gravitational force, if you got a given sign, you would go, oh, I did something wrong. Well, here you can get either sign. And you'll have 2 of these for homework. We did not do the rotational forces chapter, so we didn't, as a consequence, we did not do Newton's law of universal gravitational attraction. But what do you know about the force of attraction between 2 objects out in space? The further away 2 things get, the bigger the attractive force between them or the smaller? Smaller. Until we can get them to a point where they're so far away that they're not really attracted to one another at all. Because gravitational attraction is proportional to the inverse of the square root of the distance between 2 things. We've had a lot of inverse square relationships recently, haven't we? Electrical force is the same. And the equation for electrical force electric, I'm just going to say F-E-L, this is Coulomb's constant, K sub C. I'll give you Coulomb's constant. That's a given always. Times Q is what we use for charge. The charge of the first thing times the charge of the second thing over the radius between them squared. Can you guess what the units for Coulomb's constant are? Use your dimensional analysis skills. Okay, so we're told that the electron and proton of a hydrogen atom are separated by about 5.3 times 10 to the negative 11th meters. And what the book wants us to do is find the magnitude of the electrical force that either attracts or repels them. Well, we know it's going to do what? Attract them, because they're opposite charges. And they also want to know the magnitude of the gravitational force. We're going to skip the gravitational force part. That's where the mass comes in. We're going to skip that part. So, first of all, let's list our variables. Okay, so we've got our variables listed. One place that is a really great place to screw up, just forewarning you. If you look at these charges on the proton and electron, the charge on the electron is negative, the charge on the proton is positive. But they're both times 10 to the negative 19th coulombs, because they're both very, very tiny. Don't screw up, and when you write the proton, go, oh, wait, isn't that supposed to be negative? Because that's a great place to screw up. Okay, so this is just really plug and play. Again, the thing to watch is the sign on your charges and making sure that you square your distance between them.
Make sure to use science.
Make sure to use algebra. And this is a pretty easy one to work out, so I'll let you work out the sample, see if you get the right answer, and then assign our numbers 1 and 4 on 636. Questions, comments, concerns? Is what always going to be negative? No.
Whoa, that's weird.
Oh, actually, you know what? And
oh, we're not doing G.
Right, we're not doing G.
Well, no, I was wondering why we didn't have.
Okay, remember, the electrical force is going to be positive if it is what? Attractive. The electrical force is going to be negative if it is repulsive. Okay, we'll stop there, and you're on your own homework.
Well, with that one, I'll